Dear embedded systems learners, in this session we will learn about the circuit diagram and coding related to stepper motor interfacing with AVR microcontroller. So let us start. So to interface stepper motor with AVR microcontroller, we will be wiring first stepper motor with AVR microcontroller, and then we will write the code. So here it is circuit diagram which is used for the rotation of stepper motor. Here we can see it is AVR microcontroller. There are four pins which are being used, PB0, 1, 2, and 3, which are four pins of port B. And this is unipolar stepper motor, one of three types we discussed. And remember that unipolar stepper motor has six number of leads. That this is winding A, this is winding B, winding C, and winding D, whereas these two are center tap terminals which are connected with 5-volt DC. So this 5-volt DC is applied to center tap, whereas the four-step sequences are applied with these windings A, B, C, D. So question is, what is this here? It is actually an integrated circuit ULN2003. It is used to run properly the stepper motor because AVR microcontroller pins are not capable to provide the required current to run the stepper motor. So to boost the current or to amplify the current, this IC is used. So we can see that this is a IC which is in between the two main components. So it is a stepper motor driver IC, which provides high current which is required to move stepper motor. So next here it is actually the task which is example 1 in this book. So task is that we are to interface stepper motor with AVR microcontroller, and like we have connected the circuit like this. Exactly, the circuit is complete now. And but before the circuit connection, obviously we need to identify the terminals of motor. So this is a main step before using stepper motor, that we are to identify ourselves the six terminals. So there is no any written tags or labels on winding A, B, C, D or center tap. So we are to do ourselves. So this is very important point. So first of all, we are to identify which terminal is A, B, C, D or center taps. Then we will move forward to connect this with driver and microcontroller. So objective is to write a code for the rotation of this motor. So in this example, the motor will rotate continuously. That is, it will not move for specific let 360 or 40 or 300 degree. It will just keep on moving and so on. So the main steps before moving forward is to identify the terminals. So one method is to use ohm meter to measure the resistances of leads. We can simply identify this by using the common principles of electrical circuits and wires, that if we will connect let this winding with this or this, then there will be no infinite resistance, there will be some resistance. Whereas if this resistance is measured with this let accidentally, we measure these two first of all, then they will be showing infinite resistance because there is no any connection. Similarly, this wire will be infinite with these two wires, whereas this winding will give lesser resistance with this terminal as compared to this one, because this is in between the two. So in this way we can identify the windings. These four windings are major to identify. We can name them accordingly A, B, C, D, according to our own choice. But importantly, these two are to use as center tap terminals. So first step is to identify the leads. Then these common wires are provided with the 5-volt supply, which is this one. And then the last step is to connect this motor with AVR microcontroller through this driver, which we have discussed, which is basically a current booster or motor driver, which will provide enough current. Let, for example, if we don't have this driver, then we can use transistors, which will be shown in next slides. So transistor amplifiers can be used, but importantly, in addition to transistors, we also have to use diodes along with those transistors to save the motor's back EMF uh, towards AVR. So to avoid the back EMF spikes to, to go to AVR, we avoid this through the help of diodes. So that is another solution to use transistors and diodes, whereas in this IC both requirements are satisfied. There are internally the transistors as well as diodes. So we can use either this IC or transistors and diodes. So in this way, our circuit is now complete. Next, we will discuss the coding of this task such that the stepper motor, which is unipolar stepper motor, will keep on rotating continuously, but according to its step angle. Let it is if it is the motor of step angle 2, then it will keep on moving such that in first step it will move to 2 degree, then 4, 6, 8, 10, and so on up to 360 degree, and again keep on moving to 2, 4, 6, 8, and 360 degrees and so on. So before coding, we will be discussing the few AVR instructions which are specifically assembly language instructions, because we will code this task in assembly language, and we know that every microcontroller has its own specific assembly language. So we will be discussing the few instructions which are used in this coding in our example we are implementing. So first of all, there are two instructions. One is LSL, which is logical shift left instruction, and another one is LSR, which is logical shift left. Sorry, it is logical shift right. So this is a printing mistake. So actually both are similar, but difference is that this instruction shifts left. That is, if there are 8 bits in our register, that our register is R0, there are 8 bits. So by shifting left means the most significant bit, which is B7, is shifted left, and it will be saved in the carry flag or carry bit of status register. This is important point. So all other bits are shifted likewise towards left, and by doing so, the last bit, which is in fact least significant bit at right side, will be vacant, so that is filled automatically with 0. So this is also important, that 0 is put in the vacant position. Similarly, the left logical shift right instruction does it in opposite direction, that it moves all the bits towards right, and though the least significant bit is actually copied to the carry flag bit of status register. So this will be utilized for further logic. This is important to note. And all other bits are shifted right such that the most significant bit, which is B7 of the register, is now filled with 0. It is same as we did in the left shift operation. So these are two instructions. Other instructions are next. So the next instructions are BRCC and BRCS. Out of these two instructions, actually we will be using this instruction in this example, but this is actually the similar one, so discussed here also. So BRCC is actually the instruction which is branch if carry cleared. So branch mean the jump instruction. So this is actually the relative branch or relative jump conditional instruction, that based on some condition uh, the cursor or control of the program is jumped towards some other location. So at what condition it depends to jump? It depends on the carry flag. bit. So carry flag bit is actually one of the bit of status registers, as we discussed in last instructions of shifting left and shifting right. That shifted bit was stored in the carry flag bit of status register. So this instruction will be checking the status of that carry flag. If the carry flag is 0, then it will be jumping it, then it will be branching. And if the carry flag is 1, then it will not jump. So then it will move to the normal next instruction. So there are actually two possibilities after each instruction when it is come across with BRCC. Either the control will jump to some other location, or it will just execute the next instruction which is coming in the sequence. So if carry flag bit would be 0, then it will jump to some label which is put here, and if it is some non, if it is carry flag is 1 or set, then there will be no jump, so it will be executed the next instruction. So same is the case with BRCS, but difference is that now the branching or jumping will take place if carry flag bit is set. So jumping depends on again the same bit, but if carry flag is 1, it will jump to some other label which is put over here, like this one, like this one. This is name of the label, like here it was label name. Label is actually the tag of any line, which is the indication that this control should jump to this line, which has instruction of no operation, but actually it is tagged with this label. Similarly, here the jumping is done according to our logic, whatever it is. So in this way we can use these conditional relative branches. So we will be using only this one in this code. So next instruction is BRNE. So BRNE is the instruction which is about branching if not equal. So what is not equal? It is branch if not equal, that is the 0 flag bit of the same status register. So status register has different number of flag bits of different types. One was the carry flag bit. No, it is the 0 flag bit. So this instruction operates such that it is also conditional relative branch or relative conditional jump instruction, and it jumps if the 0 flag has 0 value there. Otherwise, it will not jump, it will execute the next instruction. So BRNE also is used. Usually it is used to implement the loops, as we know that in higher uh, level languages like C, we use loops for a repetition of some task. And in assembly language, when we want to use the repetition, as in this instruction, we want to repeat forever the movement of stepper motors, definitely we should use the loop. So this loop is implemented with the help of this branch if not equal instruction. So the logic is very simple. We will discuss in the example, and this is also example given in the appendix that can also be followed to further understanding. So the coding for this task to rotate stepper motor, which was discussed in figure 9, in which we discussed the interfacing of stepper motor with AVR microcontroller through the motor driver IC. Now we discuss the code which is in assembly language to run actually the stepper motor continuously. So the motor will be moving continuously. So first of all, uh, we know that this include is a library file which is specific to the microcontroller, as we are using AVR32. So we use the corresponding line to include that library file. Next, the highlighted part, which in short is just to initialize the stack pointer, as we are manipulating with some data while we are applying some pulses or sequences. So we are to initialize the RAM. So the RAM and high are and RAM and low are initialized with stack pointer. So this is a common 4-line assembly language code whenever we want to initialize the stack pointer. So next, in these two lines of assembly language, we can see that it is the instruction of LDI, which is load instruction, and the instruction is actually the copy of this immediate data into this register. So R20 is general purpose register. So this is source value, this is destination register. So FF, which is hexadecimal, we know that this is notation 0x for hexadecimal number. So FF, which is all 1 bits of 8-bit number, is being copied into this R20 register. And why we did this? Because actually we wanted to set port B as output. As we know that to make port B as output, we are to set this DDRB, which is data direction register, uh, um, related to port B, is to be 1 1. So we are setting all the bits of this register as 1. So we are moving or copying the data which was shifted from here to 20. Now we are copying that same data into DDRB register. So actually limitation is that we can't move the immediate value to directly to this DDRB. So we are to use first any general purpose register like R20 or maybe any other from R0 to R31, and then we are sending this to this register with the help of out command. Okay, so these are two instructions for setting port B as output. Now our port B is output. Obviously the stepper motor is an actuator and actuators are output devices. So as there is no any sensor, only actuator is being used in this task. So the pins should be the configured as output pins. So remember that as we discussed that there will be 4 pins will be used from microcontroller PB0, 1, 2 and 3. But here we have set all the 8 pins of this port as output. So practically the interfacing of 4 lower pins 0, 1, 2, 3 will be used. So next part we will be discussing is about the loading of step sequence. So we will be loading the step sequence of this task in such a way that uh, we will load the 4-step sequence we discussed earlier. So loading step sequence mean we are loading the hexadecimal value 06, which is 8-bit number actually. 6 is equivalent to, we know that it is 0, 1, 1, 0, and 0 is equivalent to 4 zeros. So this 8-bit number is being copied into R20. The same register is used again. We may use any other register, but here same register is being used because that was actually one-time use in the previous step, which was setting output port B. Now the sequence 6. So out of 4-step sequences, this is one step 6. So if we remember that there was actually the 4-step sequences. So 4-step sequences are used. So only one of the sequence is being used here. Then we will keep on changing to next sequences step by step. So if we go back towards that slide of sequences, it was 6 over here. So it was step number 3. This is 6, 0, 1, 1, 0. So we are starting from this sequence. So no choice is that if next sequence is step 2, then motor will be rotated in counterclockwise direction, and if we choose to apply next sequence as 0011, which is step 4, then it will be moving in clockwise direction and so on. We will be moving ahead. So again, coming back towards the our discussion about code. So here the shaded path in this block, which is greenish block, we are actually doing all this stuff in which we are applying different sequences. Here we know that out command is to move the values of our 20 register into port B. So now we are moving this code, which was step 3 in 4-step sequence code. Step 3 sequence is being sent to port B. So at output port B, we are sending value 0110, which is step 3 of 4-step sequence, and that will be transferred to stepper motor ultimately. So in this way, this code is being applied to stepper motor at its 4 windings. In the next line, as we are to change the sequences stepwise, so next we will change such that we will be using this LSR command, which we discussed in the previous slides. In this slide, actually we are logically shifting right. So this is the process. This was our code 06. This is 06, 6, and this is 0. So overall, this was applied to port B. And right after that, we are applying this command LSR, which is logically shift right command. So our bits are being shifted towards right, such that the least significant bit is copied to carry flag bit of status register, and all others are shifted right, and the most significant bit, which is rightmost bit, is filled with 0. So at this step, it is being shifted right. Why we are doing this? Because now we are getting the next step sequence, which is step 4 or step 2, whatever it is. Either we want to use clockwise or anti-clockwise direction. We will check towards which direction we are going in this code. So after shifting right, we are getting this sequence. So we can check whether this code is for step 2 or step 3. So let us uh, check the step sequence. So it was given over here that this is actually step 4. So after this, which was our initial step 3, we are now applying this step 0011, and in this way we are actually going towards this direction. So our stepper motor will rotate in clockwise direction. So the task will be executed such that the motor will be keep on moving in clockwise direction. So next, after shifting right, this is command we discussed, BRCC, branch if carry flag is clear. So if carry flag bit, this is clear, that if it is 0, clear means 0 and set mean 1. So as it is clear, so if it is clear, then we will do something, and if it is not clear, no, it is not clear. Sorry, it is clear. So if it is not clear, then we will branch or jump to the label L2. L2 is this one. So this line is actually jump. So it is just a jump of one line, skipping of one line. It may be more than one line. There is no problem for controller to jump to more than one or many lines. So obviously there is a limit, but here we are jumping towards L2 label if there is no carry. And here the case is that we have no carry. So we will be skipping this line. So skipping this line, which is OR command. So in this command, actually we will be doing, if there would be some carry in next steps, we will see. We will be taking OR function of 8 hexadecimal value with R20 value, which is our previous value. So, but in this case, there was to skip or to branch. Branching is same as skipping. So we will be skipping to this line instead of this line. And what is this? This line is about recalling delay. So this is also another jump, but it is not a conditional jump. Like here it was conditional jump, it was depending on the carry flag bit, but here it is just absolute jump. So we are just jumping to this label delay, which is over here. So why we are going towards this line? Because now we want some delay. We will pause on some time so that the motor speed can be controlled accordingly. So this delay function will determine how fast or how slow the motor will rotate in the our clockwise direction according to its steps continuously. So in delay, actually, this is learning of the loop instruction, how the loop instruction is implemented in assembly language. So here another register R16 is used. In this register, we put the value hexadecimal 50 value through this instruction, load instruction. Then we use no operation, that we are doing nothing. This instruction does some delay only. It does nothing with some data, but it wastes some time if that is required to generate some delay. So this is simple method of generating delay. Other methods we know that are using timers, which are proper method to generate delay, but no instructions are wasting some time, that is generating some delay. After two NOP instructions, we are decrementing this value. So whatever it was 50, after this instruction, which is DEC decrementing R16, so this value will be decremented one time. And this instruction we also discussed branch if not equal. So this instruction is also a conditional jump which depends on the zero flag of the status register. And zero flag actually becomes one if the previous instruction, which was decrement, does operation in such a way that the answer is zero. But here we know that we are just doing first time the decrement from 50, so it will not be zero. So because it is not zero, so we will, so branch if not equal, so it is not equal to zero. So we will be jumping to this label which was given with BRNEs. So it is conditional jump to move to this line again. So we are coming back at this line. So again, no and no two times in delay will be generated. And after that, we will be decrementing again and so on. This way, the decrementing will be continuing such that after uh, repeating this task again and again until this R16 becomes 0, then this branching will not be occurring and we will be moving towards this instruction, which is return instruction. So after return instruction mean we will be going back from where we came over here in this delay block. So we will be going back to this line. So at this line, we will be again going to rjump L1 and rjump L1 command will send us back towards this line. So in this way, we will be having apply one step of the four-step sequence. So in this way, the first sequence was applied for some time. This sequence was this step 3, 0, 1, 1, 0, and now we have came back to this step, which is uh, L1 through R jump. This is also absolute jump, so there is no any condition, just R jump jumps to the label wherever it is, and note that jumping may be downward or forward or reverse. Here we are jumping again backward or in upper side. So L1 is the point or line where we apply different step sequences. So till now the R20 has this line, this step sequence 3, and now we are going to change towards next sequence. So how we will do this? If we notice that step 3 is 0, 1, 1, 0, and we can get step 4 if we move all these bits towards right. Okay, so shifting right serves the purpose of clockwise movement. So here again we are using LSR. So whatever it was here in R20 will be shifted towards right. And after shifting we get this one. No, second time shifting will be such that no our this bit, last bit here, which is least significant bit, will be moved toward to a carry flag bit of status register. This is important. In previous first shift right, it was 0 in carry flag bit. Now the condition has changed. So after shifting this, we will have the carry flag bit with 1. So after this, when we come to next instruction, which is BRCC, which we have discussed, which is branch if carry not clear. So it is jumping if carry is not cleared. So what it means that if no carry skip next. So but here it is carry no. So we will not be skipping. In previous step we skipped to L2, but now we will be doing this step, that is we will not be skipping. So in this step we are taking OR function of whatever in this R20 is this one after shifting right. So we will be taking OR function with hexadecimal 8. So this is the first term of this OR function, and we are taking with 8, which is this 1000, and all higher bits as 0. So by taking bitwise OR function, that is 101000, so we know the OR function, logical OR function. So we will be getting this net result which will be stored in R20. So after doing this OR function, the result is stored in R20. This is important. So now R20 has this uh, bit which is 1001. So after getting this 1001, uh, we will be going towards the next line, which is R call delay. So again R call delay. So R call delay is the function which is same as we did previous. So there will be again some delay generated in this block. Same delay will be generated as it was previous, and after that we will be jumping back towards this line which was delay, and then will come to next line which is R jump L1. So we'll be coming back to this line and so on. So in this way we keep on moving and the step sequences are changed. So remember that these steps are implemented and these are sent to the port where the interfacing motor is attached. So in this way this step keeps on, and we again back here and the process continues forever, because this is the process forever due to this R jump L1. So this jump is making this function as the forever loop function. And note that this is also a loop function, but it is limited. It is according to some value of 50 in 16, because this is just for limited delay generation. So here our loop function is generating some delay, and through this R jump L1, which is again and again being executed, we are getting the purpose of rotating the motor forever. So there is a question about whether is it possible to move this stepper motor for a specific angle instead of moving continuously. So yes, this is possible. Think about it, how we can do this, that instead of jumping forever this loop, we will be jumping for specific number of times, as it was discussed in the example in which we calculated that to move for 80 degree, it was required to implement the code for 10 times. So if it is to move for 80-degree rotation, not forever, then we will apply the four-step sequence, this one, 10 times. And for that times, calculate that how much time this jumping should be implemented. After that, we will be getting our desired rotation. So in this way, this is important question, how we can modify this code for a specific degree rotation to this stepper motor. So next we will discuss further. So this is for the higher current requirement if we are interested to use transistor instead of the driver IC, then we will be using this scheme of Darlington pair transistors to get more current. Here our the terminals will be connected towards AVR microcontroller. These four terminals will be connected with PB0, 1, 2, and 3. And after this, these terminals are connected with stepper motor winding A, B, C, and D, and its common terminals. So these six terminals are towards motor and these four towards AVR microcontroller. So next we uh, go through this circuit, which is complete circuit for interfacing motor with AVR microcontroller. How it is complete, that here we can see that in addition to this motor driver which provides higher current to move this stepper motor to this AVR microcontroller, we have also used opto isolator. So opto isolator is another IC. One of the choice can be ILQ74 model. Here we can see that opto-isolator is actually the device which works on the principle of light. So here transistors work on the basis of light. So why we use this? Because in this way we isolate. So opto-isolator actually isolates two parts of circuitries with the help of optics or light. So here we have isolated this circuit, which is motor, which can generate back EMF when it stops or changing currents. So actually we wanted to isolate this motor from this AVR, so this motor cannot damage the AVR with the help of this opto isolator. Otherwise, it can provide any back EMF towards this controller and it may be damaged. So it is a safety device for this complete circuit. So next, uh, in the topic, we just discussed at last the example 4 of the book, which is actually the control of stepper motor through the C language code. So instead of assembly language, we are using C language, and objective is bit change. It is no another problem such that no, there are two requirements such that the motor should be rotated clockwise when there is a switch SW if it is with zero value. So we know that switch can be either 0 or it can be 1. So if switch is with 0 state, then step motor should rotate clockwise continuously or until it is at 0 state, we may say precisely. And if switch is at 1 state, then the motor should start moving in another direction, which is counterclockwise direction. So in C language, we know that these are starting lines in which we define the crystal oscillator frequency. We include libraries, basic libraries of IOs and delay. Then in the main function over here, we do the port setting in these two lines in which we set DDRA as 0 No, interestingly, we have also the sensors are input type because no are also used in addition to motor. So switches are connected at port A pins. So we are applying 00 to this port, as we know that by applying 00 we configure the port as input, and if we apply 11 which is FF in hexadecimal, we make the port as output. So DDR-B, so B port is output, A port is input. So there are two switches only actually being used, but we have done all the pins of uh, port A as input. So after that, the while function is used. In the while function, we have used the condition such that it is true forever. So forever mean it will be executing until there is the state of the switch in the same position. So in the first state, we know that to read the input status of any port, here our input port is A, we use pin A register. So whatever will be the pin A status register, we will take or check this by applying with taking AND operation with 80 hexadecimal. And if this is such that answer is 0, if this is not true that AND function provides us with answer 0, then 0 is equal to 0, then condition will be true and we will be executing this sequence. So these are sequences, four-step sequences, 66, CC, 99, and 33. And if we are uh, checking, so after 66, CC, 99, so we will be knowing that what is the sequence in this way, that after 66 and CC, here it was after 66 it was this one, after this 66 and then this, so we are applying actually in this direction, so it is actually upward, so counterclockwise direction is being used in first if statement. So in this way, after this we are applying the second step and then step 1, so in reverse direction. So in the reverse direction, mean counterclockwise direction. So counterclockwise direction is being implemented in this block when switch was 1, because being 1, this will create answer 0, and 0 equal to 0, it is true. So this will be counterclockwise direction, and if switch status is changed to 0, then the answer of this would be 1, and 1 is not equal to 0, so it will be false. So we will be executing else condition. So in else condition, the code is this one. In that code, actually the same four-step sequence is being applied, but in the downward direction, 66, after 66, 33, 99, and CC, and now it will be moving in clockwise direction. And importantly, we can see that in between the every application of step sequence, we are calling the delay function with 100 millisecond delay, and we can change this obviously to any desired value. So in this way we can change the speed of the motor. So we have discussed the content from this book. Take care.